Our next speaker is Mohamad Kazem Shirani. He is a postdoc at the Department of Statistics in University of Florida and currently a research fellow in the Reinforcement Learning Program. Mohamad will join University of Georgia as assistant professor in statistics in the coming year. Mohamad.
Thank you, Prasad. Hopefully you can hear me.
Yes, we can hear you.
Yeah, okay, thank you. Yeah, so this is a short explanation about the linear quadratic reinforcement learning problem. In number one, we have the dynamics of the environment. So basically the problem is that this is a decision-making problem dealing with an environment which is unknown. The uncertainty about the environment is being reflected in equation in number one. The linear dynamics, which maps states and actions to the next state, actually. And this is actually a stochastic one with noise. The goal is to maximize reward, number four, which is quadratic, which has a quadratic form of both the state and action. Because we do not know the dynamics matrices, they need to be estimated. So here's the problem. The classical reinforcement learning setting that we want to maximize the reward, and we also want to learn the unknown underlying environment. The reason for considering this problem as a classic one is being reflected in number 7, that the optimal action is has a linear form of the state at the time, and as a usual metric of the performance, regret will be considered as a gap between our reward and the reward of the optimal policy. So let me skip the details and go to the next slide, which is a very new algorithm, which has been there for only 25 centuries, which is greedy algorithm. And it's an episodic one that during every episode, we stick with some policy, some linear function of state as being taken as action. And at the end of episodes, the update of the unknown environment, matrices A hat and B hat, colored in red, they are being updated. So this is greedy algorithm. The length of the episodes can grow up to exponentially fast. The only thing is that we change this, we modify this algorithm somehow, that we that this least square estimation at the end of episodes will be a little bit modified to address the very famous trade-off of exploration and exploitation. So far, could you please go to the next slide? So the algorithm is a very classic one. The problem is a classic one. The only novelty lies in the modifications of this algorithm and in the analysis. Let me first tell you the analysis. There are 4 different modifications to balance the exploration and exploitation. If at least one of them is being employed, the regret scales as a square root of time, and also the quality of learning the unknown underlying environment is as specified there according to the number of samples. So in the interest of time, let me rush over these 4 different modifications of the greedy least square algorithm. One of them is to perturb the action by some small perturbation diminishing over time. This is number 1, and the magnitude of the perturbation is being specified there in red. The second one is randomizing this greedy algorithm by adding some random matrices to our least square estimation. The third one is Thompson sampling to form a posterior belief around the, according to the, using the data to form a posterior belief around the least square estimate, and then sampling from this normal distribution. And finally, bootstrapped in a sense that before we find the residuals and the estimations of the unknown dynamics according to the data, we use these residuals and the estimation to form some new fake data and use the fake data to draw some bootstrap approximation. These 4 modifications are actually solving the problem for us. Thank you.